Hey everybody. So in the last example, I talked about the E field due to a charged rod at some point P if the rod was set along the x-axis. And now we're going to talk about what the E field would be from a charged ring at some point far away from the ring or at some distance x. It's not that far away. The ring is radius a, which is a constant in this case. The ring is not going to change shape. And it's also not going to move relative to p. P is not going to move at all either. So there's this point in the center of the ring all the way out to where P is located. We're going to call that axis that comes out of this area. If you think of the ring in a particular plane, that would have to be the YZ plane because the x-axis is at a right angle to it, and this point P that we're talking about is some distance x away. So that's also a constant. A is a constant, x is a constant, which means if I think about some little area up here, this little tiny region of charge, dq, so this little differential charge element, the distance from this gray area down here to P is this guy's the hypotenuse, and then a and x would be the sides of that right triangle. So this radius right here is the, essentially this is the distance formula. You could also think of it as the hypotenuse of the right triangle. So you'll notice that in this example, which is from the book, the image is from the book, the E field, the little tiny differential E field from this differential charge has two parts. There's a perpendicular part down here at a right angle to x, and there's a part along x. And the angle between this radius vector and the x-axis theta. So let's work through why we talked about the components at all. So that's this example over here on the left on step A, or image A. If you look at image B, there's this little dq up here causing this vector, which is broken down into this component and an x component. Well, there's also a dq right down here, which is the exact opposite point, symmetrically placed opposite. If this is position 1, this is position 2. It's got E field right there, differential E2, differential E1. And the interesting thing, or the useful thing about the symmetry here, is that the perpendicular component from the top guy, E2, DE2, and the perpendicular component from the bottom guy, DE1, will end up canceling each other out. And the argument goes that that would be true for any two set of elements along this ring. And if you work your way along the whole thing, that all of the perpendicular components are gone. So in reality, the only part of the E field that's going to exist at all is going to be actually along the x-axis. So again, we're not talking about the E field from this thing everywhere in space. We're talking about just at this one point. And again, we're going to talk about the magnitude as opposed to the direction. It is, though, you can see over here I put plus q. The ring is charged plus q. So we know that the x component, you can actually go back to this guy and see what I mean, is obviously from P out that way. So, but again, we're only going to deal with the magnitude. So the differential E field in this guy is going to be k times the differential charge divided by the radius squared, but the radius in this case, let's go ahead and put r squared. So we're going to come back to that in a minute. And again, this is just the magnitude. So what do I mean by r squared? Well, since it's the hypotenuse of that right triangle, and a and x and r are all constants, I can say that r squared is x squared plus a squared. So this is the distance along the x-axis point P is from the plane where the ring is located. This is the actual distance from the differential charge element to where we're measuring the field. And this guy is the radius of the ring. And I know this seems like a pretty convoluted setup, but it not only could be used in a more comprehensive way, it sets us up to talk about what it's like to have a plate or a disk, I guess, of charge Q, and it'll lead us into capacitors. So it kind of seems like it's coming out of nowhere, but it actually, has implications for what it means to be a capacitor. So sort of a stepwise thing. Now, here's the other thing we're dealing with that I kind of didn't address right here, where all of the DE perpendiculars are canceling out. So the only thing we're going to be left with is DX, right? Or DEX. So we need the X component. And since here's DE and here's DEX and here's theta and this guy is also theta. If I want to find this component, then I need to multiply this by the cosine of theta. Okay, that's kind of hard to read, which is kind of always true, times cosine of theta when I do stuff, but still, let's fix it anyway. So cosine of theta can be defined in terms of these constants that I've got here, and the angle is right there, and if I'm trying to do cosine, then I'm going to do x over r. So x over r, and so I can take this thing that I've written, the x component for that one element there, and of course we're going to use calculus to figure out what the x component from all of the little differential elements is going to be, but we have to clarify this a little bit first. So the differential element, or the differential E field dex equals k times dq, which we're not actually removing this time like we did with the rod. And then cosine is, here, let's put that over x squared plus a squared, and then we're going to multiply by x over r. And you know what? Yeah, let's leave that there. We're going to need to do something else with this. So I was taking a peek at my notes there. Let's actually extend cosine equals x over r. Let's deal with, let's get this guy in there. So in other words, all I'm going to be left with is the differential from E in relation to x and a. I'm actually going to get rid of r altogether. So that would make this cosine of theta equals x, but instead of divided by r, divided by x squared plus a squared to the 1/2 power. So the square root of this. So I'm taking the square root of this. X squared plus a squared to the 1/2 power, which means, and this is actually where I needed this to go, the differential E field in the x direction is equal to k times dq, still haven't gotten rid of that, divided by x squared plus a squared. Let's put in parentheses, so it'll be easier to deal with what we're doing in a minute here. And then x over x squared plus a squared to the 1/2. So I know you guys are better at algebra than I am, so you can see I can combine these two things in the denominators here into, here, let's actually rearrange the top a little bit too. So I've got k times x times dq. Yeah, that'll work. And then I'm going to combine these two polynomials, x squared plus a squared. Now it's to the 3/2 power. And that's my differential E. Okay, so that's helpful in that, let me flip my notes over here, guys. It's helpful in that I've now got constant in k, constant in x, there's x again, a, and then if you look at this thing, if you can kind of peek ahead a little bit, when I go to integrate this and find the total E field in the x direction by integrating both sides, the only differential piece I'm going to have is dq. And so yeah, let's leave it there for a minute. So the integral from 0 E field to all of the E field in the x direction of dex is going to be the integral, and I'll come back to the limits here in a minute. Wait, let's move all the constants out first, because we're allowed to do that. So all of the constants are going to be as follows: k times x over x squared plus a squared to the 3/2. And then I've got the integral of dq from 0 charge to the entire charge q, capital Q. And again, we're doing like we've done before, capital Q represents the entire charge and dq is the charge element. So that means that the E field in the x direction, I love how easy this turned out to be, because sometimes starting down a calculus path, you know, you think you're doing very well, and all of a sudden you get to a point you're like, I don't think this is where I want it to be, and you got to start over. So it's nice when it actually behaves the way it's supposed to. So now I got k times x times q, that's a q, all divided by x squared plus a squared to the 3/2. And it seems like a really weird result, but k, x, a, and q are all values that we know. So you can actually figure out the E field by just knowing those values. So this result is now a general result for a ring of charge. Let me make a box. Don't you like to make boxes around your answers? That's terrible. That's much better. That is ridiculous. K times x times q over x plus x squared plus a squared to the 3/2 power. Okay, in the video about the rod, I said what happens if the distance away from this. So let's look at our picture again. If the distance P away from the ring is really, really big compared to the size of the ring. So if the distance P, or the distance X, for how far the point P is much, much bigger than A. So what happens? What does this thing do, this expression do, if X is much, much greater than A? Which means that point P is a really long way away and the ring didn't change size. So in this expression down here, if X gets really big, then A becomes irrelevant, and X squared to the 3/2 power, notice I've got an X on top, this X squared to the 3/2 power becomes X cubed, and then an X over an X cubed becomes X squared. So not that this should be all that surprising, but the E field in the X direction for a ring of charge, some really long, at a point P really long away from that ring of charge, turns out to be K times Q over X squared. Well, approximately that, right? What we're saying here is that X is big enough that the A is actually irrelevant. So, and it looks like a point charge, which is what we saw with the rod. So a really long way away, this thing collapses into looking like a point charge again. So that's exactly what we wanted to see. All right, that one was a little bit more clumsy than the last, but hey, we got there nonetheless.